Welcome back all. Today's topic is to measure or characterize the dynamics of encapsulated devices. This applies mainly towards MEMS devices. Let's start off with the motivation. Why would someone want to do it in the first place? So the capped MEMS, most of the MEMS devices are capped, and there are several reasons for it. It could be just to protect the device as it's installed or during the slicing and the dicing from the wafer. It could also be to reduce the overall form factor. There are reasons for that. There are several MEMS devices that work under certain pressure conditions. Some work purely in vacuum, and these are done to control parameters such as damping, the Q factor, things like that. So, and it's also used as, a vacuum reference. So there are several reasons why a MEMS device is capped, but that's where we stand on, the motivation behind it. And the answer from us, from Polytec, was to come up with this groundbreaking new system. It's again falls under our MSA family that's been around for 25, 30 years now. But what we call this MSA IRIS goes through the silicon cap and measures. The components would look very similar to people who have used our MSA systems. And the main difference is the camera we use and the laser source we use so that we can go through a silicon cap. So with that, background, of course, the overall goal is to measure through this cap device. And on the right, I have a little diagram that shows what kind of parameters we can handle, the gap between the MEMS device and the SI cap, or the thickness of the SI cap and the thickness of the MEMS device itself. But yeah, I mean, the challenge was, of course, to make sure that we are capturing the dynamics not only of nothing else, just the MEMS device. So that's where all the engineering and, of course, the awards that followed, were to suppress the signals from other surfaces. So once it is set up, it is no different than using our standard MSA, as you'll see in the example that follows. So we have a 2-axis MEMS accelerometer here. This one has both in-plane and out-of-plane modes. So we use laser Doppler vibrometry, of course, for the out-of-plane modes, and we use stroboscopic video microscopy for the in-plane modes. So let's, kind of go through some basics. So just so you get a sense of size here, the comb fingers are 3 microns in width here. The spacing is about 14 microns. And here we go. So let's look at the in-plane first. This is with the stroboscopic video microscopy. And I mean, the first, there was a peak at about 2 kilohertz, which is what you are seeing here. It's fascinating that, I mean, if I hadn't told you, you wouldn't know that this measurement was actually through an SI cap is what we are measuring here. So here's one example on the in-plane side, and the resolution, as I point out here, is in nanometers. Now let's look at some out-of-plane results. I want to go through a few of these, going from several kilohertz to a megahertz. Again, when you look at this super high resolution, the noise floor is sub-picometer, orders of magnitude below picometers. In this particular case, we had 6,000 plus points on the surface. And you can see it's a very high sort of modal density type object as well. But this is 194 kilohertz. Then I got a couple of examples of a close-up view. You can see it better here at 355 kilohertz. Again, these are measurements using the MSA IRIS. That is one of our latest offerings. And finally, going megahertz plus. Again, you can see the high spatial resolution plus the clarity, the cleanliness of the data. Also, hope it comes out of this video. So, we are here. We have systems here. If you think this is something that might be worth exploring, well, please reach out. You see some information here, and we'll be happy to work with you. Thank you very much for your time. I look forward to hearing from you. Until next time.